Right, so it's my great pleasure to be here. I really appreciate having the opportunity to talk and to follow such great speakers. I am originally a marine microbial ecologist, and it's rather telling that in this age of precision medicine that a marine microbial ecologist can now be a professor of surgery in the University of Chicago. It's a unique experience for me. I'm still putting in marine grants through my research group there, but we are primarily focused on the ecology of our bodies. The ecology of our bodies and the types of bacteria we find there, what kind of organisms are present, how they're interacting with their environment, where they come from, how they colonize us. And as Jessica pointed out, we have to comprehend our ecology of our bodies in the context of the ecology of our environment. And as Erica pointed out, that could be a farm, it could be an urban ecosystem, it could be a building, it could be the place where you're born. It really doesn't matter. We are a continuum. And this continuum leads to microbial uniqueness, or the unique level of microbial similarity between us. Even identical twins have a unique microbiome, which lends certain credence to the necessity to understand the microbiome in terms of its implications for human health. And Rob did a good job of highlighting that. I'm going to talk today about a couple of projects that we have ongoing, focused on the microbiology of our built environment, also the forensic microbiology, and the implications for this in human health care in hospital settings. So in our research in the home microbiome, where we spend the vast majority of our time, either asleep, eating, playing, or having fun, we were able to demonstrate that unique element of the human microbiome. We tracked a number of people over time, about 7 or 8 families, with daily sampling for 6 weeks in different homes across the United States. And we demonstrated in those instances that even when those families moved home, they brought their own microbiome with them, and that microbiome that they were exuding, and bear in mind, each one of you right now are releasing around 36 million bacterial cells into your vicinity every hour. So each one of you is sharing more bacteria than, especially the ones sitting close to each other, than you would have been normally. That microbial shed actually colonizes or releases these bacteria into that environment. In fact, in this instance, we can see people tracked over time. We have 3 individuals, a grown man living with his mum and dad. So that's the boy. He's about 22 years old. We'll call him a man. He's living with his mum and dad. Person 2 is the father. Person 3 is the mother. And he has 3 dogs. And we're using here an algorithm that allows us to identify the source of bacteria that we find on different surfaces. I want to focus on the kitchen counter for a second. Here we have it over time. And the kitchen counter, predominantly, the vast majority of those microbes come from the mother. Right? This is not a gender-biased situation. But there is a unique instance when the mother goes away to her sister's house for 24 hours, and the father has to look after himself in the kitchen, and suddenly his microbiome becomes a predominant source of bacteria on that surface, right? Telling gender inequality in this house. Interestingly, the kitchen floor is predominantly bacteria from the dog, or dogs, as you would expect, with still a substantial proportion coming from the mother. And that's because bacteria are settling downwards. In our research with Jonathan Eisen's group out of UC Davis in the International Space Station, we find no real difference between the bacteria on the ceiling of the space station or on the floor of the space station, because bacteria aren't being altered by gravity. They are distributing reasonably around the place. But in here, they're affected by gravity, so they're being participated out. You can also see weird little instances, such as in the bedroom, where the young man's microbiome becomes the predominant source for one evening on the floor. I won't comment. We're very interested in this, though. This ability to track the microbial organisms that we release into our environment gives us a certain forensic element. And Rob pointed this out with the keyboards on your computer resembling the fingertips of the person typing. Here we're actually able to track the microbiome of a young couple living with a lodger. This is an ordination plot like we saw before. The young couple are in blue and red here. These are their microbiome samples taken over time. And the yellow is the microbiome of the lodger. And as you can see, the lodger is significantly different to the young couple. He's actually significantly more similar, microbially speaking, to the young couple than he is to anyone else in our study, because he's sharing the same space. That 38 million microbes being released from his body is intermingling with the 38 million microbes being released from the young couple's body. And that microbial similarity is being shared. But as you can see from their nose microbiome, they're still relatively unique. We're not physically interacting with our nostrils. Well, I'm not. I can't talk for you people. But that leads to a degree of unique element there. And we're utilizing this information to actually track criminal activity. Criminal activity. There we are, criminal activity. In the microbiome of different environments. I'm not actually saying Donald Trump's a criminal. Just for anyone in the audience. So we've been working with police departments across the United States in order to actually enact or recreate home invasions. And this is my colleague Jared Hampton-Marcel, who got to spend time with the Florida PD and forensics teams as we invaded one of our colleagues' homes down there. We stole a TV, we drank some Coke out of his fridge, we hung around in the different rooms, and different burglars, in our instance, students from my lab, spent different times in different homes, in different rooms of those homes. And we were actually able to track the microbial signatures which they left behind. Bear in mind, I want you to take into consideration, they only spent half an hour in this home, and they were wearing gloves at the time. They did physically interact with surfaces, but really only by holding them up in front of their face and by shedding that microbial burden into their environment. This was covered in Time magazine, hence the article cover. I wasn't just dissing Donald. And what we can see is from this weighted unifrac plot, which measures the similarity between samples, the pre-burglary microbiome, when we compare the burglars to the home, their microbiome similarity increased, became less dissimilar, moved in this direction after the burglary. So the burglar shed their microbiome into that home, and the home started to resemble the burglars more frequently. And what's interesting is we can use this information to source track which burglar spent the most time in which room. So here, if we look at the bedroom, it's burglar number 1, who's the vast majority of the microbiome from the bedroom, and this was taken within 12 hours of the burglary. It comes from burglar 1. If we go to the dance room, does anyone here have a dance room in their house? This is Florida. They have a dance room, and it's burglar 2, who obviously was dancing. And if we go to the dining room, again, it was burglar 1 and the kitchen. And burglar 1 took a Coke from the fridge and spent a bit of time drinking it in the kitchen. And then the living room, where they both had to steal the television, their microbiome signature is pretty equal, whereas the owners has been significantly reduced. Now, this is important because if I want to have evidence, trace evidence, to be able to identify if somebody was in a particular room at a given time, I want to be able to use this information to track this. So I can say that burglar 1 had a higher probability of being the person in the bedroom at the time of an incident taking place, which is incredibly useful trace evidence. We are working with the National Institutes of Justice, which is the research wing of the Department of Justice, to clarify and add credence to these results now through a 2-year project which is working with various researchers from around the country. We are using this information to start to map microbial transfer, and Jessica brought this up in terms of the ability of the built environment to act as a disease sink or a disease source through infection. This is a young family living with by themselves, so 2 adults, 2 children, and we can track the degree of microbial sharing they have with their environment based on their physical interaction with that space. You can see that when we add dogs into that environmental context, it becomes incredibly complex, and as Erica and Jessica pointed out, the dog can play a significant role in helping to increase the microbial sharing of individuals, and so we believe dogs may be increasing microbial distance and degree. Now, we've taken this analysis into the hospital environment. We studied a brand new hospital as it became operational. The hospital is an $800 million building on the University of Chicago campus. And we tracked the microbiome on the top 2 floors here in patient rooms and nursing stations, tracking the building before it became operational for 2 months. And then after all the doctors and patients and nurses moved in, we kept on tracking the building, the air, the water, and the humans. And we can see here from looking at the floor microbiome of over 2,000 samples prior to opening, in blue, the microbiome was significantly different post-opening. And as Jessica pointed out, this is because the human microbiome takes over after opening. When all the humans move in, so do their bacteria. And we're utilizing this information to track the increase in similarity between a patient and their room over time. This is the important point I want to make, and I'm finishing here. But when we looked at this, number one, when the patient moved into their room, they were more susceptible to picking up bacteria from that room than they were by day 2, when they had equilibrated, microbiologically speaking, with their room. So we need to be careful of that instance. When a patient moves into the room, they're more likely to pick up bacteria. More importantly, if the patient had taken antibiotics, they were significantly more likely to pick up bacteria from their room. However, and I want to make this point very, very clear, in over 380 patients that we analyzed, at not one instance was the bacteria they acquired from the building linked to any of the diseases they acquired in that environment. And it's not just because I'm trying to protect the hospital from charges of hospital-acquired associated infections. There just wasn't that link. All of the bacteria those people suffered from in terms of pathogens were already present in their body when they came into that hospital. And we've been utilizing that information to develop a tracking system to understand the microbiome of people as they come into the operation theater, before they have their operation, so that we can understand what treatments to give them when they're undergoing an operation to prevent the likelihood of bacteria become pathogenic. We've actually developed a novel therapy which we should give to the patient during surgery, which significantly reduces the likelihood that their own bacteria will turn against them, become pathogenic, and attack them. But in order to give them that therapy, we have to track their microbiome, understand what they have in them already, and determine whether they are likely to undergo this a shift from a normal microbiota to what we call a pathobiome. So I will leave it there, because I'm already slightly over time. Thank you.